Hi everyone. In this lecture, we're going to be taking a look at magnetism. In the last lecture, we took a look at light, which gave us our first look at an electromagnetic wave. And we spent a lot of time looking at light and how that works. And so now let's look at the magnetism part of that. So let's take a look at magnetism. So what is magnetism? Magnetism is a force that is going to occur when you have electrons spinning in the same direction in a metal. So electrons are in constant motion. We know this because particles are in constant motion. Let's think back to the kinetic energy. When all of those electrons are spinning in the same direction in a sample of metal, you get this magnetism that occurs. So all electrons in motion possess a magnetic field. So whenever electrons are moving, that's going to create a magnetic field. That's why if all of them are moving in the same direction in a piece of metal, you have a magnetic metal. So electrons, we could refer to electrons as tiny magnets. So those electrons are going to rotate on their axis along with the fact that they're orbiting, moving around the nucleus. Don't think about orbiting like literally moving around like a planet, but they're in this electron cloud around the nucleus of their atom, but they are rotating on an axis. And so when they're doing that rotation, they're spinning literally in the same direction. That's when we get this magnetism. But why are all atoms not magnetic? Because electrons are paired, and typically they spin in opposite directions when they're paired, and so this cancels out the magnetic field. So one is spinning a right hand spin, one is spinning a left hand spin, and so it cancels out. But magnetic fields of electrons orbiting nuclei are also random. Because of the fact that the electron motion in most nuclei is going to be completely random, and so you overall have no magnetic field. They're canceling each other out. So that's why all atoms are not magnetic. So most materials are not magnetic as a result of that. So most materials are not. Some are, on the other hand. Some materials are magnetic, some natural magnets. So if we think about materials that have unpaired electrons and that all of the magnetic fields of those electrons are aligned, then what you're going to have is a magnet. Things like iron, nickel, and cobalt have atoms with unpaired electrons. And so when they have these domains of electrons that are moving in the same direction, that's when you're going to get magnetism. So for the entire material to be magnetic, all of these domains have to line up. In other words, all the magnetic fields have to line up. And when they do that, then you get a natural magnet. Magnetic fields have poles. Just like when you think about a bar magnet, it's got a north and a south pole. And that's because what you've got is the motion of the electron. So poles always come in north and south pairs. And the field lines go from north pole to south pole. That means that you've got this field moving from the north pole of a magnet to the south pole of a magnet. So the strength of magnetic field, that magnetic field, whatever the magnet is going to depend on how close the lines are together or how far apart they are. If the closer they are together, the stronger the magnetic field, or let's see, the lines are closer together, the weaker or the farther apart they are. So farther apart, you're going to get weaker and weaker fields. You've probably seen, and you probably know, you've probably experimented the fact that like poles repel each other and unlike poles attract. So if you have two magnets and try to put the north poles of the two magnets together, they are going to repel each other. However, north and south pole are going to pull together. So north and south poles will pull together, north and north poles will push apart. So if the fields are always going from north to south, so if we put the north end of one magnet together with the north end of another, they're going to repel. Now, if we were to take a magnet and we were to break it apart, everywhere we break it, you're going to get new poles forming. So if we have this particular magnet right here and we broke it apart, I have severed the south end from this north end, and so the new end of this magnet is going to be south, And since I severed it here, I've cut the north end off of this south pole, and so the new end is going to be north. And so the same thing would happen here. So if we think about Earth's magnetic field, so Earth's magnetic field, so the magnetic compass points northward, which means that in a magnetic compass, you actually have to, we set it so that the magnet itself is south, so it's pointed to the north pole of the Earth, and so they're attracted to each other. So it's telling you something about the magnet itself. So the needle points north because of Earth's magnetic field. Well, north is going to repel north, and south is going to be attracted to north. So the actual magnet of the needle in a compass is going to be the south pole pointed to the north pole, and that's going to be pointed to the north of the Earth. So Earth's magnetic field is shaped and oriented as if a huge bar magnet were inside the Earth, going from north to south. So geographic north pole is the axis of the Earth's rotation, and the pole is used to determine direction of true north on maps. Magnetic north is slightly off from that, but not a lot. So the magnetic compass does not point true north because of the fact that the north magnetic pole and geographic north pole are actually in two different locations. They're not far off, but there is enough so that that's going to create an issue, and so we have to watch that if you were trying to use that for absolute navigation. So the differences in the difference there is called magnetic declination. So magnetic declination must be considered when navigating with a compass. So your compass is not going to point true north, although depending on where you're located on the Earth, that may or may not make a difference. Which is why actually it's much more accurate to use satellite navigation today rather than a magnetic compass. So Earth's magnetic field, when we're looking at a map and it shows how many degrees east or west of true north a compass will point in different locations, and so this is going to give you an idea of true north versus magnetic north. So depending on where you are in the United States, this is going to give you, this map tells you how far off of true north magnetic north is. So the further away you are from magnetic north, it's going to tell you how far away true north is. So if you're over here in the northeast part of the United States, depending on where you are, you could be 18 degrees. Your compass could be pointing 18 degrees west of true north. If you're way over here, it could be pointing 22 degrees east of true north. So it all depends on where you're located. So you're going to be pretty close. If we're like where we are, believe it or not, our compass will be pointing pretty close to magnetic north where we're located. So depending on where you are, you're going to get a different view of magnetic north. So electric currents also create magnetism. Well, that makes sense. Remember, moving electrons create magnetic fields. Well, moving electrons is also electricity, which means that an electric current will create a magnetic field. So moving currents produces a magnetic field. This is why we have electromagnets. At some point in time, you may have made an electromagnetic magnet by wrapping a coil of wire around a nail and then running electricity through it, and then that actually causes a magnet. And then when you turn off the electric current by unhooking it from the battery, then it's no longer a magnet. So an electromagnet can be turned on and turned off depending on the current. Now there are a couple of different things that you could actually do here that could create a true experiment that you could do with students. You could change the material of the nail. You could change the strength of the battery.